Hello, I'm Max Naylor-Marlow, final year PhD student in the Dyson School of Design Engineering, and today I'll be giving a talk about thermal gradients within lithium-ion batteries. So my work mainly focuses on thermal gradients within packs, specifically parallel cell strings, but I'll also be giving an overview of some of the other work on thermal gradients we've done in the group over the past few years. As we know, cells generate heat during cycling, and so in most practical systems, some form of thermal management is required. This is usually achieved using either air or liquid cooling, but any form of thermal management that rejects heat to the environment will lead to some sort of thermal gradient in the system, which will then have an impact on the performance and lifetime of the device. You can reduce the magnitude of this thermal gradient, but that will come at a cost, and so this leaves us with a question. What's the impact of a given thermal gradient? What magnitude of the thermal gradient is acceptable? And what decisions can we make during design to minimize any impacts it will have on the system? So as we know, inside a lithium-ion battery, we have many layers of anode and cathode, all of which are connected in parallel. Any externally applied heat source or sink will lead to some sort of thermal gradient inside the cell, as you can see from the simulations of different cooling regimes on the slide. We also know that impedance is a strong function of temperature. Therefore, any thermal gradient may lead to certain areas of the cell seeing higher C rates, as that area locally has a lower impedance, and therefore it will see a further higher heating rate due to the increased current. So it's in a positive feedback loop. This will also locally accelerate degradation due to the high rates seen in that area of the cell, which may lead to premature failure and safety concerns. At the cell level, we can see that applied thermal gradients change the cell impedance response. So in this case, via an equivalent circuit simulations, we can see that a large applied thermal gradient leads to an order of magnitude change in charge transfer resistance through plane within a cell. And these internal impedance changes, which are induced by an applied thermal gradient, lead to the cell behaving as if it were hotter than the mean cell temperature would suggest. So in the figure, this shows measurements of a cell with the same mean temperature in each case, where increasing the thermal gradient makes it behave as if the cell were hotter. Now this is due to the nonlinear impedance behavior with respect to temperature that we see in lithium-ion batteries. As a consequence, we need to consider thermal gradients through cells during design of thermal management systems. So, moving on to packs, which is more my area of work. We can think of a string of cells, as you find in many battery packs, as like the internal structure of a cell, with many parallel electrically connected devices working in tandem. When each cell is connected in parallel electrically, we are introducing an interconnect or busbar resistance, which forces current to vary between cells. Additionally, cells are not homogeneous and exhibit different impedance responses due to either manufacturing differences, cell degradation, or marginally different operating conditions. This can result in dramatic changes to the branch current to each cell, which is almost always unmonitored by the BMS. This can be seen in the cases here of varying the cell impedance of different branches of a 6P pack, where increasing the impedance of branch 1 improves the current balance of the cell string, while increasing the impedance of branch 6 dramatically increases the imbalance of cell currents. So you can see that cell 6 sees a much higher peak current. In a pack, these high peak currents will lead to localized heating, which may in turn locally accelerate degradation and lead to the deviation of state of health between different cells over time in the pack. This current variation depends on a number of factors, including the cell chemistry, pack topology, and operating conditions. However, the interconnect resistance ratio, defined as the interconnect resistance divided by the cell impedance, is a key factor in driving these heterogeneities in current. As we can see, increasing this ratio increases the imbalance within a parallel string, and the degree of imbalance increases with larger parallel strings. This is less of a problem for higher impedance cells, for example many cylindrical cells, as the interconnect resistance is generally small, but it is an issue with ultra-low impedance cells, and today it's common to find cells with less than 5 milliohm impedance. Under a convective cooling regime, modelling shows large differences in cell heating within a parallel string, where the maximum and minimum cell temperatures vary significantly over the duration of a discharge. Initially, the most heavily loaded cells heat rapidly, but as the load is eventually redistributed to the initially less loaded cells, the temperature rebalances. However, in this case, this means that certain cells within the string will be spending extended times at higher mean temperatures, which will lead to accelerated degradation. Thermal gradients will also affect pack performance, in this case simulated for a 6p pack. As the cell impedance drops at higher temperatures, losses are smaller, and therefore it's possible to extract more energy from a given cell within a pack, which has an impact on the energy density of the pack, especially at higher rates. Adverse thermal gradients, meaning the hottest cell being closest to the pack terminals, mean we sacrifice pack energy density, while the opposite thermal gradient would lead to a relative increase in accessible capacity. This is due to voltage cutoffs being hit earlier due to state of charge imbalance within the pack. As we can see, increasing the thermal gradient in a positive direction will make the pack behave as if it had a higher mean temperature and will allow more energy to be extracted from the pack, harking back to the results earlier for the single cell. Ultimately, again, this results from the nonlinear impedance behavior of lithium-ion batteries with respect to temperature. And as a consequence, this means the configuration of a thermal management system should consider thermal gradients to extract maximum energy from a pack, as small changes in, for example, positioning or flow direction can allow percentage point improvements in energy density. So now moving on to how thermal gradients affect degradation at the pack level. Degradation of a lithium-ion battery is primarily a function of several factors, including temperature, current throughput, C rate, and calendar age. And thermal gradients at the pack level influence all of these but calendar time. Thermally driven current heterogeneities will change the current throughput, peak and mean C rates that a cell sees within the pack, and therefore all of these cells within the string will see differing conditions, which will increase the state of health deviation over time, which is undesirable. For the same 6p pack we saw earlier, we can see that changing the direction of the applied thermal gradient changes the degradation rate both cell to cell and for the entire pack. And changing these conditions has a large impact on the rate of cell capacity loss, which is highly sensitive to the operating temperature. Maintaining the same magnitude of the thermal gradient applied, but reversing the direction, leads to a predicted 9% increase in the rate of capacity loss from that pack. However, there is a balance. By reducing the mean operating temperature, we sacrifice peak performance at the start of life, as again, hotter cells reduce losses and allow extraction of more energy from the pack. Moving on to some of my ongoing work, we've developed a new test bench to allow controlled degradation experiments on multiple packs to run simultaneously under selected operating conditions. We chose a 1s2p pack topology as it allows us to practically test multiple smaller systems and generalize results. In this system, we use Peltier elements to control the temperature of both major surfaces of the pouch cell, which allows the application of thermal gradients in a controlled way to validate models and diagnostics at the pack level. This is ongoing work. We're currently degrading 6 separate packs under different conditions, but the early results show the impact of both thermal gradient direction as well as the mean temperature and magnitude of the thermal gradient is significant and is working to validate prior modeling. We'll be continuing this work over the coming months and are planning to provide a detailed look at degradation within parallel strings under applied thermal gradients soon. In conclusion, thermal gradients can have a significant role in accelerating degradation of both cells and packs above the expected rate, and thermal management system design requires the consideration of any induced thermal gradient, as localized hotspots may lead to accelerated degradation in certain areas of the pack. During design of thermal management systems, designers should include considerations of how the thermal management system interacts with the pack given its topology, as it's possible to use the thermal management system to increase both the performance and lifetime of a battery. And with that, thanks for listening, and I'll be happy to take any questions.